in this screencast I'll explain the origin of Euler's method. Now to start with, we just need to outline the basic problem that we're trying to tackle here, and that is that we have an ordinary differential equation of the form dy by dx equals some function of x and y. We're also given a boundary condition so that when x equals 0 we're actually given a value for y. And the aim of this problem, what we're trying to find out, is how y varies and changes in relation to x. Okay, so the first step in this is to find the starting point. So if we have y and x axes, we can plot our initial point. So when x equals 0, we've got our y0, and we can get this point on the graph. And that is, of course, from our boundary condition. Next, we need to work out the gradient at this point, and to do that we can simply evaluate the function f of x, y. And we do that at x equals 0 and y equals y0. So we evaluate the gradient of, and we get f of x0, y0. The next point is to draw a line through this point that follows the gradient at this point. So here we have a straight line that goes through this point and follows the gradient of that point. The next step is to actually take a step in x and y. So we go along this line and we decide to get to a new point, and that becomes our x1 and our y1 point. So we've taken a step along that gradient, along that line that we've drawn, and we get to a new point. Now I should point out that this is assuming that the gradient does not change during the step, and the reality is the gradient will be changing, and that's why Euler's method is only an approximate method. Okay, step 5 is to work out the graphical gradient, and we do this by thinking about rise over run. And the rise here is from y0 to y1, so we have to take y1 minus y0. The run is to go from x0 to x1, so we have to do x1 minus x0. Step 6 is to equate these gradients. So we've got the gradient graphically, but also if we remember from before, the gradient at this point and between these points is f of x0, y0. So we can set those equal to each other. So we've got f of x0, y0 equals y1 minus y0 divided by x1 minus x0. Step 7 is to rearrange these. So first of all, if we take x1 minus x0 over to the left hand side, we have this equation shown here, and then we can add on y0 to both sides. So y0 plus x1 minus x0 times by f of x0, y0 equals y1. Step 8 is to tidy this up. So first of all, let's say that one step in x is going to equal to h. So h equals x1 minus x0. So we can replace x1 minus x0 with h, which we've done here, and we've just flipped this equation over as well. So we've taken the left hand side to the right hand side and the right hand side to the left hand side. So what we've got now is y1 equals y0 plus h times f of x0, y0, and also x1 equals x0 plus h. So these are the two formulas that we need to take a step in y and to take a step in x, and this is basically Euler's method. This is the formulas that we need for Euler's method. If we just make this a little bit more generic, to go from yi, from any particular value of y at position I, to take one step in that to yi plus 1, we have to add on h times f of xi, yi. So this is just making this more generic using these I terms, this little I counter term. And also we've got this term here, so to take one step in x, we go from xi, we add on h and go to xi plus 1. Now also just a final note, Euler's method, as we said before, assumes that the gradient remains constant during the step, whereas higher order methods, such as second order Runge-Kutta methods, they actually attempt to compensate for the fact the gradient is changing during the step, and they have extra terms in there that try to make up for that and give an improved answer, and that's why those higher order methods give it a better answer than Euler's method.